szívlesz, én nyílsikve bangat boş, patiyada jem boş. Okay, so until now, you know that we have discussed the, wait a second, board just like this. Okay, present. Okay. Now, thank you for notifying the presence. Okay. So the last time we were discussing about the geometric aspect or the help that the vectors can provide to us to understand the geometric aspect of space, or how lines and planes are located in space. And we covered we did some examples regarding these. And the most important thing, it was that a line M1 would be defined as P plus TV. Okay, so this would be a line. To define a line, we need, let's say, two vectors. And I want a feedback from you whether the board looks good. Okay, I hope this is a good view. And so this would be a line, and the plane, let's say this one with a capital P, this would be defined as a constant vector P plus TV plus SW. Okay, so we need a single direction vector to define the direction of a line, and we need two vectors to define a plane. Now, if you have any question, we can go over we can discuss again the equations of lines and of planes. And allow me just 1 second. Okay, so today we're going to talk about the systems of linear equations. Okay, so we have systems of linear equations, and now we know that the linear equation is one where all variables are to the power 1. Okay, so we don't have x squared plus y cubed, but every variable is to the power 1, and this equation can be represented in this form. We can have, for example, a1 x plus a2 y plus a3 z. This is equal to a constant d, or let's call it d1. So here, this is how this is one linear equation. But often if we notice here, we have three variables. Okay, so three unknowns. Let's call this one three unknowns. And normally, whenever you have an equation, the standard is that any student first looks for what is given and what is to be found. Okay, so you are given some value, you have to figure that out, and the next question is what you are going to find. Okay, so this is the more essential. So in this case, what is written on the board, you are provided with some unknowns x, y, and z, and you need to find those. But is a single equation enough to define all these three? This is one question that we are going to work on. Now, you already have the knowledge actually to answer this question, which is the following. So this equation, if it has three unknowns, what can this equation define? What can this equation define?
Three-dimensional line.
Say it again.
A three-dimensional line.
Well, a three-dimensional line, if it is a line, it cannot be 3D. A line is 1D, okay? You could say, think for a little more. Do you remember last time, or during this week, we've also been dealing with equations of planes, okay? In the equation of a plane, we had all the three variables, x, y, and z, because they are defining how x and y and z are going to change. And probably this equation, we can write this as this. You can write a vector A, inner product with a vector x, this is equal to D. So in fact, if we are given only this, this is like the equation of a plane, okay? Because we have x, y, z, and we're telling the interdependence between these three variables. And you know that the equation of a plane, it looks like this, okay? Just as a short reminder, let's assume for a moment, this is like a side note and a reminder. Imagine, for example, that we have this, we used to write it like this, and V, this was equal to D. N can be equal to 3, 1, minus 1. The vector V can be x, y, z. And the D, it can be equal to 2. Okay? So what is the equation of a plane which is defined by this normal vector and this other variable? It is this equation. 3x plus y minus z is equal to, sorry, this is equal to 2. So far, we call this one the equation of a plane, okay? So we know this, right? I hope we are all good with this one. So this is the normal vector to a plane, and this is completely equivalent to this one, assuming that A1, A2, and A3, we see them here, okay? Now, imagine we provide, so far, once you see this system of equations, this is a plane in 3D, okay? Let's provide another equation, and let's write this one A11, A12, A13. Now let's write A21x plus A22y plus A23z. This is equal to D2. Now, we have a second equation. What is this second equation? Based on these arguments, based on the few minutes that we discussed, this should be another plane, okay? So this is another plane which depends on the normal vector, which is defined by A21, A22, and A23. Now, what is the intersection of a plane with another plane?
It's a line.
It's a line, that's correct. Okay, so we can obtain a line if we have two equations of the planes. Now let's provide a third equation, which can be reported as A31x plus A32y plus A33z. This is equal to D3. So now I can ask the same question, probably I might get the same answer. What is this? So the intersection of the first two planes here. So let's assume we have a three-dimensional space and we have a plane that extends like this. Okay. Then we have another plane that can extend like this, and probably the intersection between these two, it's a line that looks like this, okay? And then here comes a third plane. What could be the intersection of a line and a third plane?
A point.
Or
That's correct. Thank you for your comments. So that's a point, okay? So we can assume that we have a line now, so we extend the plane, and they're going to intersect at the single point. So using just general principles of a simple understanding of space, apparently we can conclude that if we have three equations of three planes, we can determine a single point, which is defined as we can determine the solution of this system. And the solution is to determining the correct x, y, and z. Okay, and do you see the board well?
Yes.
Yes.
Okay. So
Can you shift the camera a little bit to the right? Because there's
you mean turn it this way?
Okay, here is better. We see. No, stop.
Okay.
We can see all the table. Okay.
Okay. We can always adjust. So apparently we have three equations of three planes, and it looks like we can conclude to finding the correct solution. Now there is this is a system of linear equations. We call it a system because we don't have only one. We have few or more than one, and we can represent this whole system of equations by a matrix representation. Okay, so we can write here. We can say A11, A12, A13, A21, 22, 23, second row, third column. Here we have third row, first column, A32 and A33. So this is the matrix. We just multiply this with the variable, okay? X, Y, and Z. And this is equal to D1, D2, and D3. So here, this system of equations, it is equivalent to this one here, okay? So it's completely the same thing. So this setting is the same as this one. Only that this one here we call the coefficient matrix. This is the coefficient matrix. This is the unknown. This is the unknown, and this is the answer. Well, the answer vector or result vector. Result vector. Okay, and so these two are equivalent, but at the same time we can report as the third representation, which is this A, which is the coefficient matrix, times the unknown vector x. This is equal to D. So it looks like we can write in a simplified form all this complex system of equations. But the A, it carries all the coefficients, so we need to have detailed information about those. And the matrices are very wonderful ways to represent complex expressions. And as we said before, we said that this was a tool that was developed by physicists to keep in order a large number of equations. For example, there is also anyway, there is another example where physicists analyze the curvature of space-time in a simple matrix equation. They can write down 256 different equations. That's how they do it, because it's a combination of space and time, etc. But it's just a tool, I can repeat this again, to elegantly write down relationships of many unknowns. Now, but one thing that is very essential for us is the following. Is the relationship, maybe let's use here, it is the relationship between the number of unknowns so the number of unknowns and the number of equations. So this is something that you should never forget. And now when we talk about the number of unknowns and the number of equations, we can simply state that if we have 4 unknowns, we need 4 equations, at least 4 equations to clearly define or to get a unique solution for our system. Okay, if we have, so we have to have the number of unknowns, let it be n, and the number of equations, let it be m. And in this case, to get a solution, we have to have, let's say, the n, to get the unique solution. Let me say it this way: to get the unique solution, n has to be equal to m. Now, you can use this equivalently with polynomials. If you have a polynomial of order 5, how many solutions would you expect?
5.
5.
Right, exactly. Okay, so a polynomial with order 5. But what does a polynomial with order 5 looks like? We get minus x to the power 5 plus 3x to the power 4 minus x to the power cube plus 2x squared minus x plus 5 is equal to 7. Okay. So this is a polynomial of the 5th order. But then at the same time, here we have another polynomial, which is z to the power 8. This is equal to 1. How many solutions does this polynomial should have?
2, 1 and minus 1.
To the power of 8.
Well, it's an 8th order polynomial.
Yes.
So we should expect how many solutions?
8.
Exactly. So this is z to the power 8, this is equal to 1. So here we expect 8 solutions. Now, we don't want to jump from the linear algebra principles to the polynomials, but they are all equivalent. Okay, so we have 4 equations, 4 unknowns, we need 4 equations. You had 4th order polynomial, we have 4 solutions. But I can also ask you, what are the solutions here? Can you find all 8 solutions here?
Plus and minus 1.
But we need 8, this is only 2.
Yeah, 4 of them are identical, 4 others are still identical. Siç që themi rrejnë dy fishe kur det dallori 0.
Say it again, say it again.
So, ta them shqip,
Thuaj shqip.
kur det dallori 0 tek gradë e dytë themi është rrejnë dy fishe, janë dy rrejnë të njëjta. Dhe
No, you cannot say that. No, no, it should be 8 completely different solutions from each other. You cannot say it's the same rule. No, it doesn't work.
Okay, I don't know.
Yeah, so in real number space, we have only 2. It's 1 and plus minus 1, okay, in real number space. But in complex number space, we should have 8. So all the roots of a specific equation, all of them, they exist in the complex domain. Sometimes we may be lucky that all the roots can be in the real domain, but in this case, we should be able to solve this one, but this is not the topic of the day. So it's enough for us to remind all of us that whenever we see a polynomial, you know how many solutions we are expecting. And when we have, actually, when we go to the eigenvalue and eigenvectors in linear algebra for matrices, we're going to need the complex numbers for sure, because we don't always get real numbers as eigenvectors. Now, so let's move to an example. So let's assume we have x1 plus x2 plus x3 plus x4 plus x5. So we have 5 unknowns. This is 3. So here apparently we have 5 unknowns. The first thing that should come to your mind is, how many equations would I need? Well, 5, in order to get a unique solution. The same way that we gave 3 equations of 3 planes and got that intersection. Now, with this, then we can find here 2x1 plus x2 plus x3 plus x4 plus 2x5. This is equal to 4. Then x1 minus x2 minus x3 plus x4 plus x5, this is equal to 5. And we have x4 plus x5, this is equal to 4. Okay, so still, how many equations do we have this far? Okay, let's have here also x1 plus. So here we have 4 equations. We have 5 unknowns, 4 equations. Now, now, how can we make use of this information to conclude that to conclude on the final nature of the possible solution? What can we do for this? In order to solve this system of equations, we try to apply row operations. Okay, so we have to apply row operations. So we define the row operations because they are a tool to correctly simplify the complete system. Okay, to simplify and also to obtain some relationships which might tell us any relationship between the different equations. What we mean with this is that probably in these equations that we are given, there could be some redundant information, some useless information. This is one way to put it. And for the row operations, we define those as follows. So any row operation, row j star, this is equal to row j minus lambda row I. Okay. So the R stands for the row, j and I, it stands for the number of the row. And here, j is always larger than I, okay? Which means the following. We can modify the second row, so we can say here, second row, or we can call the row R2 star is equal to, so let's see for a moment, let's assume we want to cancel out this term, okay, or which is defined as trying to simplify the equation. So here, what does simplify the equation means? We have a matrix, let's write fast, what is the coefficient matrix here? We have 1, 1, 1, 1, 1, 1, 1, 1, 5 ones. We have all ones with only 2 twos here. Okay, you can write this one at the same time with me. And then we have all ones with 2 minus 1s. And finally, we have 1, 1, 1, 1, 0, 0. Okay, so this is the coefficient matrix which belongs to these. Now, in this coefficient matrix, the objective is to make this one as sparse as possible. So the objective is make it sparse. What does sparse mean? Sparse means make a lot of zeros, okay? Because if we make zeros, we remove the redundant information. I'm not sure actually which is the best way for you to see the board. Is it better now?
This is fine.
This is fine? Okay. I need to do one final adjustment, but let's do this later. So, so we need to do some row operations, and we have some terminology here. So, which is also we have to define a pivot row. Okay, a pivot row. It's a row with which so pivot row is traditionally here. This is the pivot row. If we are going to modify the second row with respect to row 1, what we can say is the following. Let's write instead of the second row this expression. We write here row 2, whatever row 2 is, minus 2 times row 1. Okay. In this case, in this expression, pivot row is the row 1. Okay. So this is how we have to modify these, and the definition of the row operations, we have this.
Why is lambda 2?
We have this row. We can also exchange rows. So we can do the following: Ri, we can interchange it with Rj. So this is doable. So we can exchange. We can exchange. We can write this first row all of ones. We can write it in the second row, and second row we can put on the first one. So these are the elementary row operations, and let's see another example. And when we work with when we try to make it sparse, and by the way, what was sparse have a lot of zeros. Okay, create 0 elements. Okay, and in order, whenever we do this, what we have to do is that we have to merge the coefficient matrix with the answer vector. So here, this is the coefficient matrix. We can put here a different color. And the answer vector is going to be 3, 4, 5, another 4. Okay, so, and then as we work, whenever we apply such an operation, we would get the following expression. So let's assume that we are going to apply this one, row 2 minus 2 row 1. This is going to be, this does not change, 1, 1, 1, 1, 1. The 3 remains here, and this is here. And then we have 2 minus, so this minus twice the first one. We get 2 minus 2, this is 0. Then we get 1 minus 2, this is minus 1. 1 minus 2, this is minus 1. 1 minus 2, again minus 1. 2 minus 2, this is 0. And then we get 4 minus 6, it's minus 2. Okay? So this is how we modified the first, not modified, we simplified the matrix by using row 1 as a pivot. Now, the next possible equation is we can try to make this 0, okay? We can try to make that 0. How can we do that? We can say that row 3 star, so the new value for row 3, it can be written as row 3 minus row 1. So here we get 1 minus 1, so we just subtract from this one, this expression. So we get 1 minus 1, 0, minus 1 minus 1, minus 2, minus 1 minus 1, minus 2, 1 minus 1, 0, 1 minus 1, 0, 5 minus 3, 2. Okay? Then, so we did this expression, or this equation, by using row 1 as a pivot. Then, the next possible expression could be the following. Row 4 star, this is equal to row 4 minus row 1. And what would this produce? We would have here, but why are we doing this? We're doing this because when we're trying to make it sparse to produce zeros, we want to make zeros all the elements which are below the diagonal. So if we see here, we try to draw the diagonal. This one, this is not a square matrix. It has 4 rows and 5 columns. And but we keep this in mind, and our objective is to make zeros all the elements below the diagonal. So we did these two. We did successfully. We got zeros from here. The next objective is to make a 0, this element to make it 0. Then once we do this, the next step would be to make this 0, this 0, this 0, okay? And now we are at this step, row 4 star, this is equal to row 4 minus row 1. How do we do this? This would be 1 minus 1, we get here 0, 0 minus 1 minus 1, 0 minus 1 minus 1, 0, and 0. Then 4 minus 3, we get 1, okay? So this is how we can move forward, and then the next step would be to make zeros, so these zeros, we are good. The next step is how can we make these zero, right? So we have this part, which would correspond to these 3 here. How can we make it? In order to do it, so the most important equation is rho j star. This is equal to rho j minus lambda rho I. So this is one of the essential ones. So what is the next step? The next step that we can do is that we can multiply. So here we have 1, 1, 1, 1, 1. And we can multiply the second row by minus 1. The reason we want to multiply it by minus 1 is that we want the pivot elements to be 1, okay? So the moment we try to make everything 0 here, we want to have, so we have pivot rows, okay? And we have also pivot elements. So pivot row, you can also consider it like a reference row or reference element. Pivot element. Let's make them 1, plus 1. So in order to do it, we multiply the second row by minus 1, and we get here 0. I guess this is 1, 1, 1, 0. And this is 3, and this becomes 2. Okay, then the third row, it still remains as it is. And then the question is this: how can we make this number, this minus 2, how can we make it 0? So what should be the next equation?
Multiply the second row with 2 and add them together?
Okay, let me write this one. 3 star is equal to row 3, then what?
Minus Durani.
Plus Durani.
Po.
Plus Durani.
Also,
Ose minus 2/4.
or you can write like this, it's plus 2R1, right? Let me see. Yes. So it is good, not good, actually you see that it's plus 2R1, right? But it is nice, you're going to understand me later, that to observe that this delta for the moment, this is equal to minus 2, okay? So keep this in mind, but simply state that this is row 3 plus 2R1. Okay, so this is it. So let's continue here. We get here 0. We get, let's read the row here, these values from here, and row 2, let's obtain it from here. So we get row 3 plus 2R1. Sorry, this is 2R2. This is a mistake, because now row 2 is a pivot, okay? So from this stage on, here, pivot is row 2. So this is minus plus 2R2, I think, wait, this is another mistake, 2. Okay, now it looks better. So up to this part, we had the row 1 as a pivot, as a reference with which we modify the other elements. So let's move on. We get minus 2 plus twice of this one, we get 0. Then we have minus 2 plus 2, this is also 0. And then we have 0, 0 plus 2, we get 2. Then we get 0 plus 2, 0, this is 0, 2. And then we have 2, which we read it from there, plus 4, we get 6. Okay? So I'm not sure if you can see this part of the board, but we can just, a very short reminder is that let's not forget that once we multiply this, wait a second, once we multiply this with minus 1, this becomes, this is 0, 1, 1, 1, 0, and 2. Wait a second, yeah, we wrote it over there. And this one, this is 0, minus 2, 0, 0, 2. And then, so what we do is that, let's multiply this by 2, right? This is 2, 2, 2, 4. So if we add these, we should get the third row over there. So we get 0, 0, 2, that's correct, 0, 6. Okay, so we are good. Then we have this row. So what is the next equation? To modify or to get a 0 here, we have
R4 is R4 plus 2.
R4 star, this is equal to R4, yes?
Plus 2 R3. 2R.
Minus 2R2.
Plus R2, right? Because the pivot row is still R2. So we use R2 as a pivot. So we get this next equation. So for this, we add this row here with this row here. It can be easy for us to look at this row 2 because this is the pivot now. So what do we get there? This is 0, 1 minus 1, 0, 1 minus 1, 0 again. And what is left? We have 1 plus 0, this is 1. And then we read the second row there, and the 0, 0, 0. This is another 0. And then we have 2 plus 1, 3. Here we have 3. Now, so this is the simplified version of this system of equations, okay?
4 plus, we multiply it by 2, the second row.
We multiply by 2 the second row. Why would you multiply by 2 the second row?
Well, you did it right there with the red color.
Give me 1 second.
Oh no, it was for the third row. Yeah, okay, I got it. Sorry.
Is it good? Okay, no, if it's fine, just tell me. But now, what do you see from here?
The third row and the fourth row basically are the same.
Exactly, yes, that's true. So you should pick this up, okay? Do the coupling term, okay? You should pick this up. The third row and the fourth row, they are reporting the same statement. Why is that? Let's not forget that this is x1, this is x2, this is x3, or this is the column of x3, this is the column of x4, x5, and this is the answer. The third equation is reading 2x4 is equal to 6, and the fourth equation is reporting just x4 is equal to 3. Are these two equations telling anything different? We could say no, because they are reporting the same thing, which means that we can divide this by 2, which if we divide this row, if we multiply with 1 over 2, these values will become 1, 3, right? So this will become 1 and 3. And once we have this 1, 3, we can apply another, we can have row 3 as a pivot, okay? If we keep row 3 as a pivot, what will be the next equation? The next equation, or let me think. Yes, we can simply say that row 4 star is equal to row 4 minus row 3, right? And simply this becomes 0 and 0, okay? So this is, so where is the diagonal? Let's see the diagonal. The diagonal terms, they are somewhere in here. Because the 4 by 4 matrix would end somewhere here. And then the question is, what is the next objective? The next objective is to produce zeros here. We want to produce zeros here.
Professor, can you adjust the camera a little on the left?
Sure, please. Okay. So we did the first step, which is zeroing out this the lower part below the diagonal. Now we want to zero these, and we continue a similar task. So let's erase this one. And in here, with this statement, we can say that we can use, the next question is, which one is the pivot?
2.
Which one?
The second row.
Well, you know, when we make this part as zeros, we start the pivot, we start assigning the pivots from row 1, row 2, row 3, row 4. But if we want to make zeros, this part here, we start selecting the pivot rows from the bottom, okay? You said row 2, but probably a better choice could be row 3, okay? So we could work with row 3 because we can start with this element, and first objective could be using this element here, this one, to zero out these, okay? So let's observe that part, and one thing that we can do, I think this one, we did this. So what would be the equations that we need to use? We can say that row 2 star is equal to row 2 minus row 3, okay? So this would be the other equation. So we say that I want to modify this equation by using the third one with an A objective to make this 0. And then another, so we can write this equation here. Let's write the whole thing. So this is 1, 2, 3. So that the third row, 0, 0, 0, 1, 0, 3. So this is row 3, the pivot, is the pivot. And we do this row 2 minus row 3. So here, what do we have? 0 minus 0, we get 0. 1 minus 0, it's 1. 1 minus 0, 1. And 1 minus 1, 0. And 0 minus 0, we get 0. So we have also to do this operation here, which is going to be 2 minus 3, we get a minus 1. Okay? So we completed this little task.
I have a question.
The next relevant equation is the following. We want to make this one also a 0. Okay? How can we do it? We can say that row 1 star, this is equal to row 1 minus row 3 again. Okay? And then what do we observe? We have 1 minus 0, 1, 1, 1 minus 0, 1 again, 1 minus 1, 0, 1 minus 0, 1, 3 minus 3, 0. Okay? So it looks like we are moving well. So we are sure that we have the same equations, the same information, the same knowledge is in here, but probably it is way easier how to read it. Okay, it's much easier because we have simplified it, and as we said, we are not losing any information. And if you have written the first state that from your notes that what we have here, now this looks much more elegant. Okay, so we did this. The next step that should follow is that we can use now. Yes.
Te ajo matrica lartë aty. Pse row 4 është ashtu? 0, 0, 1, 0. Dhe shuma në fund është 0. Se ne e kemi bërë që është e barabartë me R4.
Është 0, Geri, është kështu ajo. Është 0, nuk është nisha ajo, është zgaravim.
Po mirë, pse janë tëra 0 pëse?
Pa, ashtu dolën.
Po jo, s'del ashtu, dilte njëjtë me, jo as me të parës dilte njëjta.
Profesor, pse do të bëjmë gjitha 0 në këto?
Okay, so let's answer the first question. We had here 1, 3, right?
Yes.
Yes. And then we said that this was also 1, 3.
Yes.
So they report the same thing. And so let's assume for a moment, let's go back, and let's assume this is 1, 3. This is a good question. Okay. And if this is 1, 3, using row 3 as a pivot, we said that row 4 star, which means that the new value of row 4 is equal to row 4 minus row 3. Okay? If we do this, what do we get? We get 1 minus 1, 0, right? 3 minus 3, 0. So it's a result of the elementary row operations. Okay?
Po, e kuptova.
Okej, edhe çështja është që ato të njëjtën gjë tregojnë. Ti thot RK x4 baraz 3, x4 baraz me 3. Është e njëjta gjë, so take it out. Simplify the expression. So we did this, and now this, I think we answered this question. The other question was, why do we make them zeros? Well, we try, the objective is to simplify as much as possible. Okay? This is the major objective. Okay, so then this still remains the same. It's all zeros, 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 zeros. Okay, so this is how we continue. And then let's say we got these two zeros. What is the next step? The next step is what we can do to produce more zeros is to use row 2 as a pivot. Okay. And using this element, we want to produce, to make these zeros, okay? So this is how we move forward. So this is the approach, and then, let me look for a moment. So do you have any questions? So the next step, then it will be the following. Row 1 star would be equal to row 1 minus row 2, okay? And if we follow it, we'll get, but wait a second. Did we do everything correctly here? I think everything is fine. Now, here, we can modify the following as this would be 0, 1, 1, 0, 0, minus 1. And the first row would be 1 minus 0, 1, 1 minus 1 minus 1, 0. And by the way, this is something like here. 0 minus 0, 0, 1 minus 0, 1, 0 minus 1, this would be 1. Okay, so notice also this element here. So this is how the expression or the system of equations remain. So finally, this is what we get. So from this simplification, what do we obtain? How can we read these equations? Now that we are at this stage, we read this like this. We say x1 plus x5, this is equal to 1. And x2 plus x3, this is equal to minus 1. And we get that x4 is equal to 3. So, is this, if you remember, when we initially wrote all of these equations on the board, there were first of all, there were 4 equations. Now we have 3. And secondly, these are much simpler. Okay? Would you agree that this is a little, even it takes less space to write it down? So this is a simpler representation of the same information that was provided when we first wrote these equations. Okay? So what we need to keep in mind is that we do these elementary row operations. This is how we call these elementary row operation.
Professor, the simplified matrix we have now is what we get after omitting the redundant information on the first one?
Say it again. Say it again.
The matrix that we have now is what we get after removing the redundant information from the initial one that we were working with?
Yes, yes, exactly. Okay?
Thank you.
Yep, you're welcome. Okay, if you want, we can have a short break and we'll continue in five minutes, okay?
Okay.
And meanwhile,